Welcome to the second lecture of module 2 on chemical reaction engineering 1. Before going to this lecture, let us have small recap on our previous lecture. In our previous lecture, we have covered few important topic, that is introduction to the chemical reaction engineering 1. Then we considered different reactions and their classifications, different variables that affects the reaction rates. Here we have considered for homogeneous reactions and for heterogeneous reactions what are the variables that influence the rate of chemical reactions. Like in case of homogeneous reactions, we saw that the temperature, concentration, and these are the major variables which influence the rate of chemical reactions. In case of heterogeneous reactions, we have seen that the parameters which are temperature, pressure and composition. In addition to that, we have seen the heat and mass transfer effects also affects the rate of chemical reaction. Then we have different types of rates and we have seen the correlations among them, and also we have seen that the stoichiometric relationship between the rates of appearance or disappearance of the component in a given reaction. So, in this lecture we will consider kinetics of homogeneous reactions. So, the brief outline of this lecture would be the ideal reactors, then reaction rate, rate constants and its unit. Then we will discuss the elementary and non-elementary reactions, reaction order and rate law, molecularity and deriving rate law from different elementary reactions. So, let us start with ideal reactors. In general, there are three ideal reactors of which we generally considered in chemical reaction engineering. These three ideal reactors are, one of them is the batch reactor, so you have a tank and you have a starter or impeller fitted into it. Here initially you have put some raw materials inside the reactor and there is, then you closed it. So, there is no inlet or outlet for these reactors and you can start it for a certain period of time and then you can take out the products. So, this is known as batch reactor. In this case, your composition everywhere is uniform. So, composition is uniform everywhere inside the reactor, but the composition changes with time. So, these are batch reactors, and another case is flow reactors in which you have flow in and flow out. So, the other idealized reactor is the plug flow reactor, where you have a flow in into the reactor and you have flow out. you can think of a simple cylindrical pipe. So, the fluid through which it enters and it flows through, and there is no overtaking of the fluids which is behind. That means there is no back mixing in this case, that is why we call it plug flow. So, this is plug flow reactor. So, in this case no axial mixing, that is there is no overtaking of the fluids. Moving through the reactor. The other idealized reactor is continuous star tank reactor. So, it is like a tank fitted with impeller, and you have feed in and you have product out. So, raw materials or the reactants in to the reactor, mixed it with an impeller, and then you have a output. So, all these two are flow reactors. So, this is in and this is out. So, in this case it is the mixing is uniform, homogeneous, and at steady state the composition inside the reactor as well as at outside are same. So, the composition uniform mixing in this case, composition is uniform at inside the and exit of the reactor. So, the composition should be same inside the reactor as well as which is coming out from the reactor. So, these are the three idealized reactors. We will consider more details on it while designing of the reactor. Now, reaction rate and the rate constants. So, in a perfectly mixed, closed and constant volume system, or in some region of the space over which the conditions are uniform, we can write the generic correlations or the reaction, that is A plus B producing C plus D. So, we can write the rate of disappearance of A as minus RA would be equal to minus 1 by V dNA dt. So, which is equal to moles of A disappearing divided by volume into time. So, the unit we can write is mole per meter cube second. You could see the negative sign over here is the intensive measure. This indicates the rate of disappearance. That means the concentration is decreasing of the reactant. So, that is why the minus sign indicates the disappearance. Now, reaction rate for this reactions we can write R would be equal to minus R A divided by A is equal to minus R B divided by B, which would be equal to R C divided by C, which would be equal to R D divided by D. Or we can write this R is equal to minus 1 by A dCA dt, which is equal to minus 1 by B dCB dt, which is equal to 1 by C dCC dt, which is equal to 1 by D dCD dt. The coefficient, as you can see, minus A, minus B, C and D, these are the stoichiometric coefficients. And Ca, Cb, Cc and Cd are the concentrations of the different species. Now, if we see the reaction rate, we can write minus R A is equal to K into function of concentration Ca, Cb and so on. The algebraic equation that relates minus Ra to the species concentration is called the kinetic expression or rate law. So, in this case you could see this K is the kinetic constant or known as rate constant. Essentially, this is not constant, this is independent of mostly concentrations, but in case of the gas phase reactions, for gas phase reaction K depends on catalyst concentration and total pressure. However, this dependency of K on catalyst concentration and the total pressure are very less compared to the dependency with the temperature. So, K is a very strong function of temperature and which is related with the well known equation of Arrhenius law. So, Arrhenius relations where K is dependent on the temperature as K is equal to K naught into e to the power minus E A by R T. So, K naught is the frequency factor and E A is the activation energy and R is the gas constant and T is the temperature. So, we will discuss more on the determination of the activation energy for different reactions in the later of our discussion. Now, we will discuss on elementary and non-elementary reactions. Before going to this elementary and non-elementary reactions, let us introduce you which we have already discussed in the last lecture, that the different types of reactions, and we have seen there are three general categories of the reactions which happens. One is the decomposition reaction, so in this case we have seen a reactant decomposes to the product, and second thing we have seen the combination reaction, where two reactants combine and produce a product P, and third one is the isomerization reaction. And we have seen that cis A converted to trans A. But when more than one reactions happen for a particular changes to happen from the reactants to the product, then we have the kinetic expression generally consider the changes of concentration which different components produces during the chemical reactions. So, we call those reactions are multiple reactions. For multiple reaction, we have two categories. One is series reaction, like if we take A, it produces R and then R decomposes produces S. So, these are series reactions and these R we call intermediates. Now, another reactions is the parallel reaction. That means, if A can be decomposes to parallelly to two different components, that is R and S, or A plus B produces R and R plus B produces S. So, these are series parallel reactions. So, now what are elementary reactions? So, if we consider the stoichiometric relations A plus B to R, and we postulate that 1 mole of A reacts with 1 mole of B and produced R. So, in that case the rate of reaction we can write as K Ca Cb. So, in such reactions in which the rate equations corresponds to the stoichiometric equation, that means the stoichiometric coefficient for A is 1 and stoichiometric coefficient for B is 1. So, the power of the concentration term raised to 1 for both A and B. So, if that is happens, that means the stoichiometric equation and the rate equations are same. So, in that case we can say this reactions is elementary reactions. One good example of elementary reactions is that the hydrogen reacts with iodine and it produces Hi. The rate law we can write minus R H2 is equal to K CH2 Ci2. So, that means these relations correspond to the stoichiometric coefficient of the overall reaction. When there is no direct correspondence between the stoichiometry and the rate, then we call that the reactions is non-elementary reactions. That means one such example is the production of HBr from reactions between hydrogen and bromine. So, if we react with hydrogen plus bromine, it produces hydrogen bromide twice HBr, and the rate expression is RHBr is equal to K1 concentration of H2 into concentration of Br2 to the power half divided by K2 plus concentration of HBr divided by concentration of bromine. So, this reactions does not corresponds to the stoichiometric relations shown over here. So, that is why this reaction is known as non-elementary reaction. Now, we will discuss about some other fundamental of reactions. One is reaction order and rate law. So, the rate equations is generally derived from the experimental measurements, and that is based on the change of concentration of reactants or the products which are produced. So, if we consider the general rate equations, minus R A is equal to K C A to the power alpha and C B to the power beta. The exponent over here represents the order of the reaction. So, here alpha and beta are the exponent of the concentrations. So, alpha is the order with respect to A and beta is the order with respect to component B. So, the overall order of this reaction, if we consider n is the overall order, then n would be equal to alpha plus beta. So, this is the overall order of the reactions, or if we the rate of reactions K R A is equal to K into C A to the power n. So, then the order of the reaction is n. In the if nth order reaction, the unit of rate constant K we can write would be equal to time inverse concentration to the power 1 minus n. So, this is the unit of K. As I said earlier, the K is the rate constant only when we considered at a particular temperature, but essentially K is a function of temperature. So, the better term to use for K is the rate coefficient instead of rate constant. So, K we can call rate coefficient. Now, if we consider a general reaction A plus B to C, and the rate law, we can write rate is equal to K C A to the power alpha and C B to the power beta, and this alpha and beta they are determined experimentally. For example, if we consider 2 N2O5 gas, it converted to 4 NO nitric oxide gas plus oxygen gas, and the rate is given as K concentration of N2O5, that is the reaction is first order. That means, if we double the concentration of N2O5, the rate of reactions will double. So, if we triple the concentration, the rate of reactions will triple. Now, if we consider another reaction, twice NO2 gas and it decomposes to twice NO gas plus oxygen gas, and the rate is equal to K NO2 to the power 2. That means, the reaction is second order. So, in this case, if we double the concentration of NO2, the rate of the reactions will enhance to quadruple. Another reaction is twice HI gas converted to H2 gas plus I2, and this reaction is found to be 0 order. That means, the reaction is independent of the concentration of the species. Now, we will discuss another important topic, which is molecularity of the reaction. The molecularity is defined is the number of atoms or ions or molecules involved in the rate limiting steps of the reaction. Based on the number of molecules involved for a rate limiting steps, we can define it as unimolecular, bimolecular and trimolecular and so on. But the unimolecular and bimolecular reactions are common, but termomolecular reactions are very rare. One common example of unimolecular reaction is the conversion of the uranium to thorium and helium. So, this is the reactions of radioactive decay. And this is the reactions in spontaneous in nature. So, elementary steps or elementary reactions are simple steps that together make up the reaction mechanism for a given reactions. An elementary reactions is characterized by its molecularity, which is the number of molecules or particles involved in the formation of the transition state complex. And elementary reactions may be characterized as unimolecular, bimolecular and termomolecular, which I have explained before. So, if we consider elementary reactions, then it would be easy to find out the rate of the reaction, and the molecularity will be based on the elementary steps of the reaction. Unimolecular and bimolecular reactions, as I said, it is the most common in the processes. Now, we will consider rate law from elementary steps. So, if we consider elementary reaction, say A2 product, then we call the molecularity as unimolecular, and the rate law, if we can obtain from here, it would be K into concentration of A. If 2A produces products, then we call bimolecular, and we can write the rate of the reaction K Ca square, Ca to the power 2. So, this is bimolecular reaction. Now, if A plus B produced P, this is also two different reactants reacts together producing product P. This is also bimolecular reaction. And the rate we can write K into Ca Cb. And another one, if twice A reacts with B and forms product, then we can tell this reaction as termolecular, and the rate would be K into Ca to the power 2 into Cb. So, as we said, the termolecular reactions are very rare. One example of termolecular reactions is assumed to happen for the conversion of oxygen to ozone. So, oxygen reacts with nitrogen and it forms O3 plus O plus the activated complex of nitrogen species. So, this reaction is considered as termolecular reactions, but in general the termolecular reactions are very rare. Now, we will consider rate law from rate determining steps. How to obtain the rate equation or the rate law from the rate determining steps. If a proposed mechanism consists of more than one elementary steps, in that case the slowest steps or the steps where the rate is the slowest of the overall reactions is considered as the rate determining steps. So, it is called the rate determining steps, which step represents the rate law of the overall reaction. Like if we consider reactions NO2 plus CO reacting and then forming NO plus carbon dioxide, and the reactions happen in a single step. So, in that case we can write the rate is equal to K into concentration of NO2 into concentration of CO. However, the experimental measurements shows that the rate is actually K into concentration of NO2 square. So, now if we propose this step into two elementary steps, these reactions, if we propose into two elementary steps, we can write step 1 NO2 reacts with NO2 forming NO3 plus NO with a rate constant K1. And step 2, NO3 reacts with CO forming CO2 plus NO. So, this reaction is actually slow and this reaction is fast. So, this is the rate determining steps. So, from here we can write the rate is equal to K into CnO2 square. So, as we have said, the overall reaction rate must be determined experimentally or the rate law must be obtained from the experimental measurements. And if there is elementary reaction, then the rate equations can be obtained directly from the elementary reaction or from the molecularity of the reaction. Like for following examples, it forms and we can write the rate minus R1 is K C NO into C concentration of ozone. Similarly, if N2O5 decomposes and forming NO3 plus NO2, we can write as K into concentration of N2O5. Similarly, bromine plus nitric oxide reacts and form ONBr2. The rate can be written as K into concentration of bromine and concentration of NO. Now, we can also obtain the rate law from the slow fast elementary steps, like if we consider the reaction twice NO2 plus fluorine, it forms twice NO2F and the rate we can write K into concentration of NO2 into concentration of fluorine. The proposed mechanism for this we can write NO2 reacts with fluorine, form NO2F plus F, NO2F can form NO2F and the overall reaction if we sum it off, so this will cancelled out and we will have twice NO2 plus F2 forming twice NO2F. So, this is the first step and it is considered as slow and rate determining, and this is the second step and considered as first. So, the rate of reaction for this we can write K 1, say this is K 1, concentration of NO2 and concentration of fluorine. Now, rate law can also be obtained from the second step, which is slow reactions. Like if we consider twice NO plus oxygen forming twice NO2. The rate is K concentration of NO square or to the power 2 and concentration of oxygen. So, in this case the mechanism we can propose as NO reacts with oxygen form NO3, NO3 plus NO form twice NO2. So, if we sum it up, so this will cancelled out, we will have twice NO plus oxygen forming twice NO2. So, this is the overall reaction. So, from here the slowest step is the second step and this is first. So, the rate of reactions we can write. So, this reaction, the first reaction is considered to be the equilibrium reaction and hence this is rate is written as K2 into K equilibrium, concentration of NO square, concentration of oxygen, which is equal to K into concentration of NO2 square into concentration of oxygen. So, the rate can be obtained from the slow elementary second elementary steps. So, there is correlations between the reaction mechanism and the rate law. The elementary steps must add up to give the overall equation and also elementary steps must be physically reasonable, that is proposed step can occur with a reasonable probability, so that they are either unimolecular or bimolecular. As we said, a termolecular elementary steps is considered unlikely. The mechanism must correlate with the rate law, that is the rate law derived from the rate determining step must agree with the actual rate obtained experimentally. Thank you for hearing this lecture and we will continue our discussion on the reaction kinetics in our next lecture.